Okay, so it's going to be a bit of a very short session today, but I want to use every single minute I can to work on this. Um, one of the biggest questions. So my next kind of step in this is right, like take a look at the. I think we, yeah, I think that's what we did. We kind of copied that example suggestion code from last session here. And first question is like, that's really, I'm not so sure Ghostwriter is going to be able to answer these, to be honest. So do uh, next word prediction, uh, LLMs uh, need a vocabulary. It's critical. I mean, I know it seems obvious, but it's uh, like I know we naturally, like we build up a vocabulary, but then at some point in time, like we actually think of ourselves as like language models, biological language models. I almost feel like you're not like you don't really have a vocabulary as in this strict sense of like a list of words, right? You kind of have a way on how to build a vocabulary. For example, if you think of things like quick, right? Like you don't. So that's another question. So is this vocabulary like a strict list of words? Like does such a vocabulary have separate entries for things like uh, nouns and adjectives that can be derived? Like, for example, do the words quick and quickly have separate entries in the vocabulary? Because I have the feeling that shouldn't be the case, right? So in general, word embeddings are learned on a token by token basis, which means that different forms of a word, like quick and quickly, are treated as different tokens and therefore have different entries in the vocabulary. In other words, each distinct form of a word is treated as a separate unit, even if they share the same root word. However, some models implement stemming or lemmatization, which is process of reducing words to their base form. Okay. Um, that definitely kind of resonates with one of the comments from Sam Alpan, I believe. No, 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 no. Who was that? Someone else made a tweet about like LLMs are because of tokenization. LLMs are definitely not end to end. Now this kind of makes sense because it's just the more you hard code, the more complicated, like the less end to end and natural this actually feels like, right? Um, but I'm right now at the point in time where I'm like, I'm not so sure if I can trust Ghostwriter in these. Like, should I Google for someone else's opinion? Maybe I would. Uh, let's see. I need a vocabulary. Like, what do I get? Predict, predict the next word. Next word prediction. But I wanna see. Oh yeah, yeah. Then that might be a word. That's maybe um, from its vocabulary. Um, I have a very understanding of the attention mechanisms and models and the coded network. How this will produce attention weights for the word vectors based on positional codings and some other learnable parameters, query, and this can be fed to the decoder part of the network, which will also consider word vectors that have been produced by the decoder so far and influence word selection by paying special attention to particular word combinations. However, elements could produce words as their output that do not occur anywhere inside the prompt text, so they must be using these attention weights to consider words from a wider vocabulary, which could be quite large. In this case, the coder considers each part because it's like the vocabulary. It's like ChatGPT answers you in like any fucking language. Like So this considers each possible word in the entire vocabulary when producing another word. For example, I'm imagining an input layer, several thousand nodes on per word vector in combined through some operation with attention weights. Um, so that's the question. Now, after forwarding the prompt through the whole transformer architecture, the output is forwarded through one final linear layer. This final linear layer maps the output of the model back to the size of the vocabulary. If you want to predict the next letter in a message, it will, okay. It will map to 26 letters. Interesting. For each possible output token, it predicts the probability between 0 and 1 that token is the next token. For models such as GPT-4, this last linear layer maps to a 10,000 plus dimensional output. It includes Arabian, Chinese, Japanese, etc. tokens. Regarding your question, yes, each output token is considered as a possible option. Crazy. That is crazy, actually. If you think about the fact that these things actually have a vocabulary, that means like GPT-4 linear maps to a 10,000 plus dimensional. I don't think that's the way it's meant. Like it's not 10,000 dimensions, but it's like 10,000. So what's the vocab size of ChatGPT? Words are part of a vocabulary, a limited corpus of 170 tokens in the English vocabulary. Repeat the math. Okay. Whatever that is. Is this trustworthy? Oh my god. Ads everywhere. Oh god, what is this? So now vocabulary size is 40 million words. Many words, bro. Explaining the math. Okay, so so this is just someone trying to reverse or trying to kind of predict what the size of these is. Kind of increase the cut size. Only counting once when it contains many contextual meanings. We assume that GPT always able to learn a language due to word availability. Coding languages don't increase the vocab size since the keywords from a coding language based on the words the language is from. Yeah, that's true. Korean. But I'm curious if ChatGPT is using words. Very powerful because it has a yeah, that's true. Why wasn't it trained with more words? Not dictionary like. Yeah. For creating good embeddings and output that wasting training time on words you and I don't understand. Okay. Anyway, it has a vocabulary. Sorry, Ghostwriter, for not trusting your reply in here. Um, so essentially, what we're doing here is okay. So this is just what we copy pasted from Ghostwriter. So we're tokenizing the input. Can I put that side by side here? So so we're tokenizing. Okay, so we're tokenizing it a bit differently, right? So we're tokenizing the input. Maximum words, word counts, vocab size, Okay, so here there's some additional stuff like tokens and words, and then word counts, and then we're creating the vocabulary, and then assign an integer index to each unique word in the vocabulary. Okay. Okay, so that's actually interesting. It means it's gonna use the word indices actually instead of hmm, wait. But so assigning an integer index to each unique word in the vocabulary, uh, same length, the X word, convert the tokens to one-hot vectors. Okay, so it's using. So instead of using the ASCII, okay, I see what this is gonna do. Okay, so we'll implement these. So padded tokens, adding padding to each word. So essentially, the tokens. Where is that? Where's the actual encoding happening? So words, number words, maximum words, words. So this is just adding the padding, and then tokens. The Unicode. Oh, okay. So here we're encoding character by character, and so this is, and so here, assign an integer index to each unique word in the vocabulary. So what's going to happen here is we're going to just index the words in the vocabulary, and then we're going to use the index as the basic uh, the stuff that we're gonna feed into the positional encoding, which is okay. Which I guess it's okay because essentially it doesn't matter. You just need a number that represents that word. That Yeah, well, maybe it matters. Um, Maybe it matters because you know, kind of if you're using another, like if you're using the characters to represent the words, you know what I mean? Like that can add some sort of that can show some different like some you know potential correlations between words that have a similarity when it comes to the character composition of the words. Um, Whereas here it seems like you're gonna just use index or like vocabulary indices for these. Um, vocab size, line size, word length. So the input sequence is the word index. Right. Examples and targets. I have to understand better how this works. Can I print X, print Y, and then basically, oh, let me do the following. So we'll rename these. So let me rename. Let me do one thing. So let me rename these, and we'll just finish it. Cause so this is the main original, okay, and then this is basically just going to be we're gonna duplicate this file and call it main. And so what we're gonna do is basically remove all these for now, like the rest of the file. And I just want to see what's been like. So like print X. What is this giving me? Print Y. Yeah, of course doesn't work. let's just actually ignore these. And actually, let's print the input sequence. What is this? Doesn't even work. Oh God. Sorry. I'm doing this in the wrong file, obviously. I should do this in the new main, which is this one. And then basically just delete these. And then can I print X and Y? Maybe now this works. Okay, so that actually works, but it doesn't help me at all. Input sequence. Or input sec. Oh yeah, because this is, what is these zeros and ones? That makes no sense. So what is in word IDX? And okay, so that's an index. Jump 0, doc 1, cat 2, cat dot 3, lazy 4, brown 5. Okay, and then IDX word. What's in here? Okay, so that's the other way around. And then convert the tokens to one hot vectors. Convert the tokens to one hot vectors. So we're taking an input sequence. It's full of zeros, and then enumerate tokens. Okay. 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 So I get it. So what's happening here is, yeah. Okay. So if I say input, like is an input sequence, if I give it the sentence and a word, it will tell me, and then the word index. Okay, so that's just like a, yeah. This means, so if I print this stuff, so essentially this is for each sentence, right? So there's like 4 sentences. For each sentence is like just a word by word, just zeros, and kind of whatever the word is not there, and then a 1 where the word is there, right? Yes, I remember that was the actual original definition of the one hot vectors, but like this is definitely like these are actual one hot vectors as per the definition. But I remember that we were checking with Ghostwriter and kind of like I think it was okay the way that we were doing it, right? Because that just makes no it just this is a very inefficient representation. I think I would just keep it the way that we do it. I don't think they use one hot vectors. That just makes no sense for like a 14 million vocabulary size or whatever. Like you just have like a bunch of zeros and ones. It's just this makes absolutely no sense. It's a lot of multiplication you need to do. You know what I mean? Like in the main original, here what we're just doing is basically encoding the words using the characters, and that's it. Uh, and then That's what we're doing, and then we're enhancing that with positional encoding. The one-hot vectors in here, in my opinion, it just make no sense because it explodes in size. Input sequence. The model max length, back size. Okay, hopefully I mute it on time. Yeah, this makes no sense. Apply the positional encoding to the input tensor. I don't think this makes sense. I just don't think I don't think it matters. I don't think it matters as in like what the for word prediction, as in like it doesn't matter, as like it makes more sense that we like one hot vectors make no sense. I just can't believe this makes sense. So given given the scale of something like an LLM with a full multi-language vocabulary, does it make sense to use one hot vectors to represent tokens? Because size of color, exactly, it just becomes very large. They're called a binary vector. Yeah, that's what I would say. The size of the vectors also become very large, which sorts of embeddings can be used to okay. So embeddings. We keep getting back to this word. Embeddings can be used to represent tokens as they capture underlying semantic and syntactic relationships between words, which can be helpful. So, can you give me a very basic embedding algorithm and code? Create embeddings, vocab size, embedding size. So, simple embedding algorithm, create embeddings, vocab size, embeddings, NP zeros. I don't think that makes sense. What embeddings? Vocabulary size, embedding size. But that returns zero. What does the function return? No, that's not what I mean. To make code embeddings. So what are example strategies to generate embeddings? I think this is what we're doing. I just think that's what we're doing. Count-based, neural network-based, pre-trained embeddings, count-based methods. This strategy involves computing the number of times each word appears in large corpus text. Text. Neural net-based methods to learn the dense embedding representation of words. It's the word2vec, which trains a shallow neural network on a large corpus of text to learn word embeddings. Other approaches in this category include GLOVE and fast text. I think I asked this already, is the ASCII representation of a word a valid embedding technique? Does it have a downside? Any downsides? I think I've asked this already. So is it valid? Yeah, they don't capture semantic or syntactic relationships between words. It means that words and meanings Similar embeddings. Okay, I know what you mean. Okay. I know. Okay, so the problem, yeah, the problem with these is with synonyms and stuff like that, right? So, of course. Okay, that's fine. So the embeddings essentially, yeah, it might not capture, it doesn't capture like words that are spelled completely differently, but they're used or they can be used because have the same meaning. They're, of course, they're not captured. Okay, but we'll stick. You know what? I think we'll stick to these. So we'll stick to using we'll stick to using these. We will definitely not use the new main stuff. We will definitely not use that. Okay, cool. That's good progress for today. So we need a vocabulary, um, and we can just use the ASCII encoding. That's all good. So I'll either code that in between sessions or do another session later today on these. And the next step is the sequence splitting. So for these, I'm going to be using main original. Let's just do the following. Okay, so I'm going to keep the main. I'm going to keep using these padded tokens. Okay, so these for sure. I'm gonna keep using these for sure here. So I'm gonna keep the original stuff in this case. Use an auto embedding algo. So node, not ASCII, but like whatever, like character based embeddings means relationships like between synonyms. So okay, and then that's the next thing to do: split the input signals into examples and targets. That's the next to do. Okay, so far we're just going to use the same thing here. Oh, but we need to create the vocabulary, obviously. So there's another to do, which is create vocabulary. Create vocabulary. Okay, but we're going to use this new main now to rebuild the stuff. I think that's going to be the easiest. It's going to reuse the main original and just rebuild the stuff that is missing here. Okay, cool. See you in the next session.